Here's our problem. We have to find the equilibrium constant, Kc. Alright, so what is the equilibrium constant? I like to just very quickly call it product over reactants, right? So something like that, unless one of your products or reactants is a solid or a liquid, in which case it doesn't appear in our expression for equilibrium constant. But these are all gases, so these are all going to be in there. And we don't want to forget to raise these concentrations to the power of the stoichiometric coefficient. So SO3 has a 2 in front of it. SO2 has a 2 in front of it, so those both get squared. And these are equilibrium concentrations. These are the concentrations once the reaction has reached equilibrium. So let's see, do we know any of these values? We are given one value at equilibrium, but technically brackets mean concentration, so technically we just got moles, so we have to figure out concentration given this number of moles. We divide by the volume in liters to get molarity, and now we have one of the numbers we have to put in here. How do we find the other two? We don't have to use an ice table, but unless you have like superhuman mental capacities, it's really helpful to use an ice table. How do we do this? Okay, so start with I, that stands for initial concentration. C is change. E is equilibrium. Most of the time, the point of using an ice table is to figure out the equilibrium concentrations of all your compounds or substances. And there they are. And again, let's not forget to convert this 0.064 moles of SO3 into concentration, molarity. So to do that, we'll divide by the volume again. And this 0.16 is our initial molarity of SO3. And the other thing we just figured out was this 0.0375 molar oxygen at the end. So now we just have to figure out the rest of the table. And to do that, it helps to assume that we did not start with any oxygen in our container. It says, the only thing we put in there, it says is SO3. So we're going to assume we started with no oxygen, and therefore whatever we ended up with is the change in oxygen. Now likewise, we also started out with no SO2 in there, but the change for SO2 is going to be twice that of oxygen. So this change we have for oxygen, we've got to double that, multiply it by 2 to get the change for SO2. So we end up with 0.075. And we double it because of the stoichiometric coefficients here. There's twice as much SO2 being created compared to oxygen. There is also a 2-to-1 ratio of SO3 to oxygen. So the change for SO3 is going to be the same. But this is a reactant, and we are losing that. So this is a negative change. Therefore, to find the final equilibrium concentration of SO3, we're going to subtract the 0.075 from the 0.16, and we get 0.085. And the final equilibrium concentration of SO2 is pretty straightforward. We started with none, and then we gained 0.075, so that's what we end up with. And can you see why an ice table is so handy here? There's, can you imagine keeping track of all these values in your head and the ratios and adding or subtracting? But with an ice table, all we have to do is refer to this bottom column when the reaction has reached equilibrium and just pop those values in up here to the equilibrium constant that we define. And that's what we've done here. And now the calculator does the rest for us. And that is your equilibrium constant at some specific temperature that it's at.